Okay, good morning and welcome to this look at the new version of the pre-release. This is for the full A-level course. It's the second paper that has a pre-release document, and you probably read it already, and it's all about paper and how paper degrades over a period of time and how you can preserve paper, and the sort of chemical techniques which are used to preserve paper. The first thing I'd just point out about the pre-release, we're talking about one question here at the end of the second exam, and by far the most important thing that you need to do is know your A2 chemistry, to put it bluntly, because if you can do that, you'll be able to answer the vast majority of the questions. And some of the pre-release questions, in fact most of the pre-release questions, you can probably answer without having to glance too much at the actual pre-release document. However, the pre-release document does give you an idea of what that question is going to be about, and we can speculate, and that's what it is, speculation on what the questions might be on. But it's all good revision, and it's really important to have a handle on the content of the paper, because some of the questions will directly reference the content of the question, the paper, the pre-release material. And if you can quickly find the bit that you want, then that's a really good thing in an exam, because you don't want to be messing around trying to find bits of the article if you haven't already studied it. So we're going to look at some of the chemical content, maybe some vague suggestions about what might be on it. So what I'm going to do is attempt to do a bit of screen sharing, and then you can watch what I'm doing. Okay, so what we want is this thing, and we're going to go full screen. And I've got, get rid of that. So I've got the paper here on a tool called real-time board, and I've grabbed each page of it and put it into this tool. So you can see it's all about the preservation of paper. It goes on to talk a little bit at the start about what paper is, and it talks about it being a polymer. And the polymer is made from this particular monomer that we've got up here in the top right hand corner. This is beta-D glucose, and we'll come back to that structure later on. It's in some of the sample questions I've put as well, because there's all sorts of questions you could ask about beta-D glucose, because it's an interesting molecule. But a lot of this paper talks about the importance of hydrogen bonding. And so let's get a pen tool and let's go black. There you go. So it talks initially about hydrogen bonding here. So I'd be very surprised if at least in one of your three papers, if not this particular question, you didn't get asked to represent hydrogen bonding going on in something. So it would just do the classic case of water. It's a bent molecule because you've got two non-bonding pairs of electrons there. We've got delta negative there, delta positive there, delta positive there, and then you've got an oxygen here, lone pair of electrons there, there, H there, delta positive, delta negative, delta positive. So if you've got any question that asks you about hydrogen bonding, then you want to make sure that, let's just have a different color. Let's go blue. These three atoms in principle should be in a line. It's kind of linear. And you put the polarity on, and you've shown this lone pair of electrons, which is on the oxygen being attracted to the delta positive hydrogen. So if we just go across to beta-D glucose, you can see that we've got loads of this going on. So let's annotate. Oops, let's annotate our molecule a little bit with a couple of lone pairs of electrons. I'm going to pick this OH group here, but there are loads to choose from, and we could have hydrogen bonding between that and let's say the hydrogen on a water molecule like that. Okay, so there's lots of opportunity for hydrogen bonding in this molecule and other reactions, which we'll come back to. So that goes on to tell you a little bit about what paper is, and the fact it's a polymer of that monomer that I've got up in the top right-hand corner. And it tells you about additives which are used to strengthen paper, one of which is mentioned a bit later on, but one of them is aluminium sulfate. And if you imagine putting an aluminium ion into a polymer that's made of this stuff, aluminium has a pretty high charge density, and we've got lots of non-bonding pairs of electrons on this oxygen. Actually, it would have been better to put it in between these other two here, but you can see that you can get a strong attraction between these non-bonding pairs of electrons on the oxygen and the aluminium, and you can get that going on to a neighboring chain where you've got an oxygen there and an oxygen there. And this comes in color by design when it talks about mordanting, because it's a way in which you can actually get dyes to stick onto fabrics. So you have a mordant, something like an aluminium 3+ ion, which helps join the dye molecule onto the fiber. So we've effectively got dative covalent bonding here. So aluminium is forming a complex. Transition metals don't have a monopoly on complex ions. Okay, that's all I wanted to talk about on the first page. If we go on to the second page, which is here, it says paper in Europe was originally made from cellulose, from linen and cotton, and it talks about the fact that how strong the paper is depends on how many repeat units you've got, and that's typically typical of polymers. So you can plot a graph, which used to be in the old spec. I'm trying to remember if it's in the new spec. I think it is. Of chain length there against tensile strength. So TS in this context is tensile strength. I should move a bit. That's better. And what happens with tensile strength? So that's the force you can pull, say, a piece of paper or any other polymer or material. When the chain length is very, very small, when it has no tensile strength, and what happens is it gradually goes up like that, and after a while it plateaus like that. And what that's saying is that paper made from linen and stuff like that, I think it is. What does it say? Yeah, linen and cotton gives you longer polymer chains than the ones made from wood. So here we've got the ones made from wood pulp having 600 to 1,000 repeat units, whereas the ones made from linen and cotton having in the sort of up to 3,500 repeat units. And what's going on here as this the chain length increases is you're getting more. The predominant type of intermolecular force here is hydrogen bonding, because you've got all those OH groups. So we're getting more H bonding going on, bigger polymer chains, more capacity for hydrogen bonding. And you've got a rather nice diagram of the hydrogen bonding in figure 2. Okay, and the other thing that's going on as you get longer and longer chains is you get what's called chain entanglement. So just imagine you have several very long pieces of string, and you put them in a pot and you scrunch them up. It becomes really very difficult to untangle them, not because the attraction between the polymer chains or the pieces of string is particularly strong, but because the chains are literally tangled up and you would have to sort of very methodically untangle them to get them to pull apart. And that's what happens when you get very long polymer chains. They wrap around each other, get twisted together, and consequently they get entangled, and it makes the polymer stronger. It only works up to a certain point, because once you get very long polymer chains, the difference between two polymer chains which are several thousand repeat units long and one that's, say, 10,000 repeat units long is one bond. It's just joined two ends somewhere, and that doesn't make much of a difference to the degree of chain entanglement, which is why this graph flattens out once you get to a certain number of repeat units. It doesn't actually make much difference making the chains any longer beyond a certain point, because you're not having any significant increase in the number of intermolecular forces or indeed the degree of chain entanglement. But difference between 1,000 and 3,000 is going to be quite noticeable, which is why you get this difference in the strength of the papers. So you got this nice diagram of the hydrogen bonding between these cellulose chains. You might want to put in the polarity here because there's none shown. Okay, and the lone pairs, because I just mentioned that was important earlier. So whenever you do an example of hydrogen bonding, or you have to sort of draw that, then put in those two things. They're not actually explicitly shown here. You might be asked something about that. So that's what paper is. And then it talks about the sorts of things which attack paper. And it goes on about acid attack. And it says there are two principal chemical degradation pathways: acid catalyzed hydrolysis and oxidation. So in terms of hydrolysis, the mechanism here isn't on the spec, but there are plenty of examples of acid-base hydrolysis that you're meant to know on the spec. So obvious ones are esters and amides. So make sure you know about the hydrolysis of those. If it starts talking about acid hydrolysis, then it might conceivably ask you to do a reaction of those, but those reactions are likely to come up. Oxidation, we need to look at the alcohols which we've got there. And if we just go back to the structure up here, what we've got are a number of groups that we can oxidize. If we just take the glucose molecule on its own, and you might be asked, what would you get if you oxidize this? So let's just have a think about that. So you could oxidize that with dichromate, for example, in acidified conditions. So let's imagine what we would get. We're still going to have the ring, like that. The alcohol in the top right-hand corner is a secondary alcohol. So you could imagine we'd oxidize that to a ketone. The one at the bottom is a secondary alcohol. So you might imagine we oxidize that to a ketone, as is that one, as is that one. They're all secondary alcohols, whereas the one on this little branch here is a primary alcohol, so that's oxidizable to a carboxylic acid. I don't think that's what you really get if you oxidize glucose, but the point is we do have secondary alcohols in this molecule, and we do have primary alcohols, and therefore we need to sort of look at that. The other thing to point out about this molecule while we've got it on the screen is the fact that it's chiral. So we've got a number of chiral centers. So you could be asked about chirality and the fact that we can form non-superimposable mirror images. We've got 4 different groups on these carbons. The fact that it's a ring still counts as groups because it's non-symmetric. So that's why we've got the chirality shown in this particular molecule. was my credit card bill being paid. There you go. Okay, so that oxidation reactions, and we've got some hydrolysis reactions. And then it says paper can become acidic either by absorbing pollutants as sulfur dioxide and nitrogen dioxide. Well, conceivably, you could be asked about where they're going to come from. So sulfur comes from the oxidation of sulfur when you burn things like coal, and it also comes from volcanoes, and then add a bit of moisture to that, and ultimately you get sulfuric acid. Likewise, if you take nitrogen oxide, react it with oxygen, then you will get a variety of nitrogen oxides. So that one, for example, or you can get NO, or you can get N2O. And you could imagine that perhaps you've got something about oxidation numbers coming in. So that's sulfur in the +4 oxidation state, nitrogen in the +4, nitrogen in the +2, nitrogen in the +1 oxidation state there. So we could maybe have something about variable oxidation states and the fact that these compounds are all acidic oxides. Remember, this can be drawn from any part of the full 2-year specification. But one of the things it talked about earlier is the fact you use aluminium sulfate. Now, aqueous aluminium ions are acidic, and we've got this equilibria here. So this is a hexaqua aluminium ion. So, as I say, transition metals don't have a monopoly on forming complexes. This is a group 3 metal, and it can form complexes. So it's not a unique thing. So you might have to draw a complex. So that's that one, and it's got coordination number of 6. Okay, and it's hexaqua aluminium 3 ion, and this is acidic because it will deprotonate a water molecule here. So this is an acid, and water's acting as a base, and that's the conjugate acid there, and that's the conjugate base there. Okay, so we've deprotonated one of these water molecules. So things like +3 transition metal ions do pretty much the same thing as well. So we've produced this acidic solution, which then goes on to hydrolyze our cellulose. So you might have something about shapes of complex ions here. This is octahedral. Okay. What else have we got in here? And it goes on to say the beta-acetyl oxygen bridge joining the glucose molecules of the cellulose together is susceptible to acid hydrolysis. So the beta-glucose bit is this oxygen bridge that you got there. Oxidation is usually initiated by light. So if it's initiated by light, that could suggest it's a, where's it gone? Initiated by light there. So it's a radical reaction. And there's some radicals later on as well. And so what is a radical? So it's something with an unpaired electron. Okay, so representing them with a little dot like that. So there's a bit of radical chemistry going on there. And what's happening when you hydrolyze it, you're basically adding a water molecule, so you get 2 OHs. So imagine breaking one of the bonds and you end up with 2 OH groups, one on each half of the where you've broken it. That's everything on that page. Let's go down to this one. Okay, and this actually has that hydrolysis reaction shown, so you can see that we've got, this is our acetyl link here, this oxygen, carbon, oxygen, carbon bond here, and that's, you're adding water across that to leave these two OHs here. So you've literally just added water to it. So this is going on to talk about how we can preserve it. So one of the ways you can preserve it is to remove the acidity, and it suggests various things that you could use to remove this. Oops, so I skipped a page. I have skipped a page, sorry. Okay, this is a bit about chromophores and conjugated aromatic systems. So this is why things become colored, and this seems to be quite a common question to ask things about. So a chromophore is the bit that's absorbing visible light. And we're looking at explaining this in terms of this equation. Always quote this when we're talking about sort of the absorption of light and all that sort of stuff. So if you're going to absorb visible light is fairly low frequency, and therefore the energy gap is small. And what we're doing is moving the electron from one energy level to another energy level, like that. And that energy gap has to be small enough so it's visible light being absorbed if something's going to be colored. Okay, and when you have delocalization and conjugation, so you've got double bond, single bond, double bond, single bond. So you might have several sort of, like in an azo dye where you've got an N double bond, you've got a couple of benzene rings either side. You've got a lot of conjugation, so the electron energy levels are quite close together. So that energy gap, you can excite an electron from one energy level to another energy level with quite a small energy gap. So you only need a relatively low frequency, which ends up being in the visible region. There was something about that on the color by design test. So it says it contains several chromophores with conjugated aromatic rings and carbonyl groups that absorb in the near UV spectrum. When these chromophores absorb light, they can decompose into yellow-colored ketones and quinones, turning the paper yellow. So we're going from a situation where we're absorbing UV. So this is UV, and that was 300 to 400 nanometers, to something where we've got the energy levels much closer together. So this is where we've got our ketones and quinones. So we're getting all this conjugation going on. So the energy gaps, the electron energy levels are getting closer together. Whereas in the original molecules, it's sufficiently far apart that it's only absorbing ultraviolet radiation, so it doesn't appear to be colored. So this is why we're getting the yellowing of the paper, because we've got the formation of these chromophores, because we've got this conjugation going on. You've got a value of 300 to 400 nanometers. What you might possibly have to do, and it'll come up sometime, is convert that into, say, how much energy are we actually absorbing. Okay, so nanometers, that would be, say, 300 times 10 to the power of -9 of a meter. What we'd need to do is convert that into a frequency. So the speed of light is equal to the wavelength times the frequency. So that's in meters. This is in seconds to the -1, and that's in meters per second. So we want to work out what the frequency is, and you might have to do this. So that's going to be the speed of light, which is 3 × 10⁸. This is on the data sheet, divided by the wavelength, which is 300 × 10⁻⁹. And then you could use the equation E equals h mu. I mu is the frequency there, and Planck's constant is on the data sheet. And you can actually calculate the value of these energy gaps. So actually that's the UV one. Okay, if you're talking about visible light, you'd be talking about 500–600 nanometers rather than down at 300–400 nanometers. So there's a couple of calculations they might ask you about that, possibly. And then it goes on to about paper preservation, and one of the ways it does it is by neutralizing it, and it adds things like calcium hydroxide. So that's CaOH2, and you might remember from Elements of Life, you need to know something about group 2 chemistry. So it might be linked into something to do with the solubility of group 2 metal hydroxides. So calcium hydroxide is not particularly soluble. So group 2 metal hydroxides start with magnesium all the way down to barium hydroxide. That's pretty soluble, and that's only sparingly soluble. You'd only get a tiny amount of magnesium hydroxide dissolving in water. So the solubility increases down the group, which is the opposite of things like the carbonates and the sulfates, which get less soluble down the group. But they're all could, in principle, be used to neutralize this acidity. But it talks about the issue here being you're kind of soaking them in an alkaline solution, so that could make the paper sort of fall apart, and it could also damage the inks which are on the paper. And then it also talks about the fact that there's an awful lot of this stuff to preserve, and it's looking at more efficient ways of deacidifying it. And it says paper should have a neutral range here of pH 6.5 to 8. So you might have to apply this equation to work stuff out. So you might have to work out what the actual hydrogen ion concentration would be for that pH range. So where that is in range 6.5 to 8. So what's the actual range of hydrogen ion concentration? Maybe. So root into using that equation. So you'd have to sort of rearrange this. So concentration of hydrogen ions equals 10 to the power of minus pH. And there's a bit of interesting chemistry down at the bottom here. It talks about this diethyl zinc, and it tells you that it's pyrophoric. That means it spontaneously ignites, which is quite cool. So it bursts into flames, which is potentially a problem. So it's diethyl zinc, and that is got CH3CH2 minus, and that's acting effectively kind of as a ligand to the zinc. So we've got something that looks like and we've got presumably a dative covalent bond between the carbon and the zinc going on here, and you could probably imagine this is some sort of linear complex like that. But it would, I imagine these zinc carbon bonds are not particularly strong, and I suggested a combustion reaction for it, which would make zinc oxide 4 carbon dioxides, and 5 water molecules. So we get something like that going on, I think. And it tells you how it acts as an acid. It acts as a proton acceptor. So the ethyl anions are getting protonated to make ethane, and liberating a zinc ion, and you've got it reacting with water here to make zinc oxide. Zinc oxide is going to be a basic oxide, and that's going to help neutralize the acidity, I guess. And the last page. Oh, hang on. The last page is not in the same place. It's over here somewhere. There it is. That's the last page. Perfect. There we go. So it goes on about the group 2 and the group oxides and hydroxides. So things about those, their basic nature perhaps might come up again. And then it talks about bleaching it. So this is removing the yellowing, and it's got hydrogen peroxide, and possibly you might have to draw the structure of hydrogen peroxide, or perhaps a dot and cross diagram. So a dot and cross diagram would look like this. So that's hydrogen peroxide. Hydrogen peroxide is one of those interesting ones where you've got oxygen in the -1 oxidation state. Like that. And because you've got 4 pairs of electrons around each of these oxygens, it's kind of pseudo-tetrahedral. But because there's nothing in a couple of the positions, then you end up with a bent molecule about each oxygen. And because there's 4 bonding pairs of electrons there, this is kind of like the bonding that you get in water. You'd expect a bond angle of somewhere around about 104.5 degrees, because these lone pairs repel more strongly than the bonding pairs. And you've got a ion being formed here, which is this minus the hydrogen. So it's that ion there. So you might have to do a dot and cross diagram of that, perhaps, which is going to look very similar to the one that we've got there. So extra electron here is now the negative charge. So you get something like that for OOH minus, which is the ion it's talking about being made here in this particular reaction. This is a reversible reaction, so we can write a equilibrium expression for it. Like that. Okay, but you might also notice that this is basically a hydrogen ion. So you could write this as a Kc expression, Ka expression, I think. So if we take the water out of it, which is what we do when we do acid dissociation constants, we'd get hydrogen peroxide behaving as a weak acid. And I don't know what the Ka value for that is, but that opens up the possibility for a weak acid calculation. But you've got to realize that actually that's what it's behaving as here. When you do dissociation or weak acid, you don't normally show the water. So what I've done is take out the water there, and we've got HO2 minus plus H plus. So you got something like that. So there's this bit here, which is really important, and I think is a gift for a potential question. It says the reaction only producing an appreciable amount of peroxide ions in the pH range 8 to 10. So this is all about the position of the equilibria. And if you're pH 8 to 10, you've got some hydroxide ions knocking around, and that's going to react with hydrogen ions to make water. So that's going to push this equilibria this way because you're removing H3O plus. So you're going to favor the forward reaction, and you're going to promote the formation of these particular ions here, which suggests this is a very weak acid. We're not getting much of those without bringing in hydroxide ions. Incredibly weak acid. Never thought of hydrogen peroxide as being acidic anyways. So that's something to do with the application of Le Chatelier's principle of course. Okay, so we're going to favor the forward reaction. So that's that bit. And it then goes on to talk about the fact that this is more than a blank piece of paper. The fact it's got pigments on it, and you've got to preserve the pigments as well, otherwise there's not much point to preserving just the paper. And it says presence of excess iron and catalyze the oxidation of cellulose through the production of hydrogen peroxide through this Bentham mechanism. So what we've got here is transition metals as catalysts. And the key thing is here we're looking at the fact that we've got two oxidation states going on here, and it involves some radicals. It's a complicated mechanism. And so the things that allow transition metals to act as good catalysts is the fact that you've got variable oxidates, and we've got what have we got? We've got complex formation we can do. And because we've got iron 2 and iron 3, and coming up, okay, we could talk about the relative stability of those. That doesn't look much like relative, does it? Relative stability. Okay, so we're going to talk about the fact that this one here has got a 3D5 subshell, and this one has got 3D6. Okay, so this being a half-filled D orbital is more stable than this one, which is 3D6. So we've got a bit of electron propulsion and all that sort of stuff. So that might come in there. I did look up what this stuff is, and I wouldn't worry too much about it because it's an incredibly complicated ion. But there is a word here that I would suggest you know. It says chelates or chelation, and chelation is where you've got polydentate ligands and the forming rings by joining onto multiple positions on a complex. So much simpler example than this iron that they're talking about here, phytate iron. I'm not quite sure if that's how you pronounce it. So let's say you've got 2+ complex, and you could have something like an oxalate ion or ethane diarate ion. That's a much simpler example of chelation, and you could actually, that's a bidentate ligand, and you'd get 3 of those going on to form an octahedral complex. And this is catalysis. And you might have to do something where you've got the sort of energy level diagram for catalysis, I guess. So if we've got an exothermic reaction, we might have a transition state here, so we've got some complex there, and then it goes down to here, as opposed to having a non-catalyzed reaction where that's EA for the non-catalyzed reaction, and for the catalyzed reaction, EA, because it's going via a different pathway, is faster. And at some point in the exams, of course, you're going to have to define a catalyst. So expect that. Anyways, so that's sort of some of the key points, perhaps, and some of the things they might possibly ask you about. The other thing that I've got, which I'll give you in the lessons, I'll probably put in your drive, is some potential questions. So in this document here, so we'll go through that this week. But if you've had a look at the video and read some of these beforehand, that would be great. Okay, well, I think that's probably long enough now.